some elastography inverse problem itself and what we do to actually solve the problem numerically, right? So there's few aspects of numerical implementations are in there, like mesh adaptivity. So that's what I will be focusing on. So with the audience in mind, it's not going to be highly technical. So there's basically some equations are going to be there, definitely. I need them. So, and then because we're talking about, numerical methods and mathematics behind it, but it's not going to be super, technical. Okay, so I was asked about talking about my career path and trajectory a little bit. So I put a few slides in there and logos. I was actually born in a country called Mongolia, which is in Central Asia between Russia and China. So it's a landlocked country, pretty big land, but not too many people in there. So here on the left, so that's how the main capital city actually looks like right now. So there's high rises and buildings, fancy buildings like that. So, but there are a lot of places that look like actually this, right? So this is countryside. This is actually one of those small, see if you go far out in the country. So this is a university that I actually did my undergraduate degree. So undergraduate degree in applied math, so math mostly, but there's applied track in there. So computations, programming, numerical analysis. So that's what I did. And then I actually worked at a university that produces mainly engineers. And so that university I taught for a while, about 4 years, right after graduating from my program. And so then I moved into grad school. So this is actually one of those tiny villages that my parents actually live in. So my parents still live in a place like that. So with 2,000 people there. And I do visits occasionally every few years. So that's how it's an adventure to actually go from here to there, because I have to take a travel just to get to the capital city. It takes about like an average like 30 hours from here. So 3 planes, 30 hours. And then afterwards, I would be taking a train to get to a nearby city. And then from there, I would be taking a bus or some kind of car to get to a village like that. So that's an adventure. And so then after that, I did go to a university called Technical University of Kaiserslautern. So that's the one in Southwest Germany. So that's where I did some like master's program in industrial mathematics. So technomathematics or industrial mathematics, idea being that you learn math, basically how to solve applied problems that come from industry. So that was the idea there. And then after that, I moved into University of Erlangen-Nuremberg. So that's the one where I did PhD. So scientific computing, applied mathematics, that is kind of things that I did there. So I stayed there 4 years, here 3 years. So altogether, it's about 7 years in Germany. That's where I lived. And then after that, I came to USA. So after a small stop at the Michigan Technological University, I arrived here in Rochester. So I've been here since 2008. So it's been, quite a long time, actually. You don't realize how fast time is going. Okay, so my research interests, numerical analysis and scientific computing in general. So I'm interested in applied problems, mathematical models, but mainly solving problems numerically, doing simulations, deriving error estimates and things like that. So my particular specialty is actually so-called finite element methods. And I'm going to talk about this one actually a little bit in today's talk. So what is the idea of this particular method and how is it actually used to solve my problem, right? So the main thing that I'm going to be talking about is actually this one. So now many of you actually do work with partial differential equations that come from engineering model or imaging or physics and so on. So there are all these partial differential equation models. They do have parameters in them. Some of them could be just scalar parameters, numbers, but some of them also could be functions, right? So my problem that I have is recovering a parameter that is actually a function. So we call it spatially varying parameter because it is a function of the domain, function of position, basically, right? So, and so because it's an inverse problem, parameter identification problem, so you need to actually formulate the problem in as an optimization problem because there's going to be data and there's going to be data fitting, basically, right? So data fitting in a function space. So that's what this one's about. So I'll talk about these ones. So more recent things, I'm looking into stochastic models because that's something that is physically or realistically makes more sense. So they are kind of difficult area in PDEs. So it's a kind of a subfield that a lot of people specialize in, but not me. So has been a little bit challenging. We have taken some steps to work with stochastic models, but not too much, right? And reduced order modeling, so that has to do with basically improving computational efficiency of whatever method you are doing or whatever problem you're solving. So that's something that I'm currently looking into. So hasn't done much progress in that one, but that's something that I'm interested in. Okay. So here, there goes my equations or PDE system. So what is the idea here? So I have here a U, which is a function. So the bald face, that kind of indicates that this is a vector function. Okay, so that means you're going to have, in this particular one, you actually have two components if you're staying in two-dimensional. So this is going to be basically components of the displacement, x direction, y direction, right? So you have two functions. So this x stands for x, y in two dimensions, right? So here, this is my main model equation. So this F stands for external force. So you can imagine kind of a situation that I'll talk about those ones later too as well, but you're basically thinking about a situation that where you're applying a certain force into an object, right? So it could be tissue, right? So that's the force function. And so that's the stress tensor, so which is actually here. And then, so here, these two, they stand for the boundary conditions. So U is equal to G. So what does that mean? So that one is basically telling that we are specifying the displacement in certain part of the boundary, right? So your boundary is going to consist of these two curves if you're in 2D. And so on the other parts of the boundary, you might be applying some traction forces, right? So that's traction forces. That's how it's basically specified. So this H is going to be given. This G is a function that's known. So for example, the boundary part, certain boundary part is maybe pinned, right? There's no movement. Then that would be a zero function on both components, right? So that's this linear elasticity model. So here the stress tensor, that has to do with some material parameters. So here's this mu, so that is what we call shear modulus. Again, so that's elastic property of the material or object. And so this mu is going to be important. And so this lambda has to do with basically compressibility of the material, right? So if it's water, maybe it's going to be really, lambda is going to be a really huge number because it's almost incompressible. So those are material parameters, this mu and lambda. So that's how this equation looks like. So it's basically a system of PDEs, right? So you have two components in the displacement that you're looking for. So that's why you call linear elasticity system, right? Okay, so here just another kind of relation between, so a lot of the times you see in the literature talking about Young's modulus or Poisson ratio instead of the bulk and shear moduli. So the relation between them, so the ones that we use, at least in the math community, looks like this one. So the special thing that you need to take care of or look into is this one here, the way the nu is appearing here. So if the material is incompressible, what you have is basically lambda is going towards infinity, right? So lambda large being material basically nearly incompressible or incompressible, right? So this is the basically the limiting value. So nu being close to 0.5 is going to indicate that material is going to be nearly incompressible, right? So if it's exactly 0.5, that's incompressible, right? So those are kind of terminologies that you see in different literature. So the inverse problem that we are dealing with is basically, so this is what's behind. So here the idea is that we have the goal of this kind of problem, studying this kind of problem, is that by looking at the measurement, by taking the data, which is displacement, right? So what you are trying to tell is you're trying to tell something about the material properties, right? So that's the idea. So cancerous tissues, they are known to differ by their elastic properties very much from the soft tissues. For example, they are stiffer. And so on average, 5 to 10 times is what I've seen in literature. So if you can find out the locations of the tissue, right, so that are stiffer or contrasting material properties, then that's something that could help somebody to diagnose maybe there's cancerous tissue is present, right? So that's the idea. So soft tissues that we are going to talk about, they are considered nearly incompressible. So that means you're going to be looking at this new value or the Poisson ratio close to 0.5, right? So we are not going to be fully compressible. That's pretty clear when you're talking about tissues, but it's going to be nearly incompressible. So that's the assumption that, some of the biomedical engineers, they work on this kind of problems. Some from the math community do as well. Okay, so here are just a few things. Again, nothing super complicated because we are talking about nearly incompressible case. You saw that how lambda is going to be extremely large, right? So the scale between this lambda parameter and the mu parameter, that's going to be very, very different. For example, in our case, we take like really large value. Lambda is like 10 to the 6, right? And the mu is going to be, depending on the situation, mu could be, intense, right? Or something like 4, 5, 6, right? That's the range we are talking about. So, and having that lambda really big is actually creates the problem if you try to solve that linear elasticity system numerically by using standard methods like linear finite elements and so on. So that's the problem. So we need to make a slightly different formulation by introducing a new variable that we call pressure. So here's a divergence of u, that's going to be nearly 0. And so this lambda is really big. So there's this balance in there. So you change your equations a little bit so that you can actually use method that does not give you trouble. So what does this mesh locking mean? Mesh locking means that you are going to get solution or representation of displacement that doesn't actually make sense physically, right? So that's the reason that we need to have a slightly different formulation. Doesn't create too much problem, so that's just a slight change. And so those of you who are interested in numerical methods for PDEs or use them, finite element method is one of the methods that are really good for solving PDEs. And there are methods like finite differences, which some of you actually use. And so there's finite volume, and there are other methods as well. So the idea of finite element method is something that I want to talk a little bit about. So this one is basically the idea of finite element method is to replace this differentiability conditions, and that's required from the U displacement. In this case, what we require is that U displacement components, they need to be differentiable continuously twice in every point of the domain, right? So which is kind of really restrictive. And so the idea of finite element method is that to relax those conditions, because there are situations where displacement components do make complete physical sense, but may not be differentiable, right? It may not be really smooth. So what we do is we basically change the equations into an integral form. So that goes basically like this. You multiply these equations by a so-called test function, and you integrate over the domain, right? And then, so by using integration by parts, or the parallel of that in multi-dimensions, you basically ended up having a requirement like displacement components have to be smooth, but doesn't have to be too smooth. So like required maybe just continuously differentiable, right? So maybe not twice. So that's the idea. So because what we need to do is a lot of the time when you have a model like this, you cannot solve this analytically, right? And so you need to use numerical methods. So that means we need to do some sort of relaxation, right? So the integral form or the weak form is what we need to do before we start discretizing, and then we can have something that can be solved in computers, right? Okay, so here, just kind of connecting how those equations look like. I was talking about how we use so-called integration by parts in multi-dimensions. So if you multiply the equation that we had before by a test function that's called V, then you're going to have something like this, right? So now this is an integral equation that has to hold in a function space for all possible test functions. So, and that's something that we cannot solve again. So integral equation, and then we cannot make sure that it is valid for all those functions from the function space, right? So now, what we're going to have, so there's not going to be distinction between two different problems. What is a forward problem and what's the inverse problem? So forward problem basically means that you know the F, the force function, right? And you know the boundary conditions. So this one is actually written for a boundary condition that's 0, that's completely pinned boundary. So, and then now your job is to basically find out the displacement components, right? So displacement vector function. So that's what we call the forward problem or the direct problem. And I'm going to just talk about the forward problem a little bit so that before I move to what the inverse problem is, right? So the idea there is now, when it comes to the forward problem, right? So the one that I was just talking about here, you need to solve this numerically. And so that's something that's also required for my inverse problem as well, right? So you need to actually solve the forward problem at every iteration, right? So this is an important component of whole the solver building process, right? So here, how does this work? So you typically start with, should I put a picture on here? So you basically start with discretization of your domain. So in this case, the particular thing that we are doing is that we actually partition the domain into rectangles. So now you can just kind of imagine having maybe square or rectangular domain, so that would be really easy to kind of partition to small rectangles or square, right? And then now basically after that, what you need to do is you need to make sure that you choose set of basis functions, because we're working on a function space. And then you express basically your displacement and as well as pressure in terms of those basis functions, so that the final problem that you end up solving in discrete form is basically just a problem of finding these scalar coefficients u or p, right? So it is going to be eventually a linear system, really large scale linear system, because the number of basis functions that depends on how many little squares or rectangles do you have in your partitioning, right? So that's how this finite element actually works. Okay, so here again, so one thing that I'm doing here that most people who are just solving the forward problem do not do. So they do not actually need to do something like that, but I need, because this mu, the stiffness or the tissue stiffness, is the parameter that I'm actually looking for my inverse problem, right? So that's going to be a parameter that needs to be discretized as well, right? So here again, so these are basis functions, right? And these are the coefficients or the coordinates of this function with respect to my basis function. So these are, again, just scalars, nothing else, right? So now what you can do here is, after using this discretizing step, what you end up is you end up with a system that looks like this. So this is just a large scale system. And so that's the unknown coefficients that comes from my displacement representation. And so this one has to do with the force function, basically, in this case, right? So that's basically the discrete problem that you're looking at when it comes to that initial, this elasticity system discretized. So this is what you end up with, right? So this K, this depends on the mesh, right? So how many little squares you have, or rectangles you have, or triangles you have. Sometimes there's triangles as well. And so depending on that, the size is determined by that. And then, but essentially it's just linear algebra problem, right? So in this particular case, because we have a vector problem, okay, that's in the next slide, I guess. So this is basically how it's going to look like in two-dimensional case. Now, I just drew, really coarse mesh with how many? 1, 2, 3, 4. So 8 by 8. So only 64 little squares. And then, so on each of those little squares, your function of two variables is going to be basically approximated by a plane, right? It's piecewise linear. That basically means a plane. So all of these are pieces of plane, and then if you patch them together, this is how the approximation is going to look like. So now you can imagine that situation that if you increase the number of little rectangles or the squares, right, you're going to get something that's much more smoother and resembling more like a nice and continuous function, right? So without any, sharp bumps like that. So that's not going to happen. And then, so in this case, if you have, for example, piecewise linear representation, so the number of variables in the linear system, so that U vector that you're seeing, and that's going to be, in this case, actually 128 by 1, right? So because we have one component, U1, that's going to have 64, right? The other one, 64, so you have 128, right? So it's relatively small. So now you can imagine the situation that what we want is, we don't want really something like that, so that's too rough or not accurate enough. So what we need to have is, typically you have hundreds of thousands of little rectangles, right, to resolve things properly. So that's how this one looks like. So again, just a tiny example. So if you're interested in looking at how that particular large matrix looks like, so this one looks like here. So this one comes from one of the terms in the system. And here, these two are related. So, and that's the one that comes from another one of the terms. So the only reason that I have this one here is that I want to emphasize that the parameter that I'm going to be looking for eventually is going to be actually kind of hidden in that particular top left block, or in the A matrix. So I haven't told you much about what this M is about, but you're going to see that in a few minutes. Okay, so time-wise, so the stiffness matrix, this is called stiffness matrix because it comes from the engineering problem. all this finite element stuff. That's what a lot of engineers actually do. So here, this is just a library, finite element library that we have taken, mainly used for forward problems, but we can also build inverse problem solver by using this one as well. Okay, so here, just a kind of a situation that you might see in more realistic kind of situations. So this one was, for example, a two-dimensional domain. And so this new is 0.4999. So that's like nearly incompressible situation. And you can kind of relate these, what's going on, the displacement wise here as well. So what you're doing here is that these two boundary pieces, so the left and right, they're actually not moving at all. So there's no body force, no traction on the sides. So they're freely moving. We are allowing, and then the bottom one, top boundary, sorry. So that's the one that's actually pinned. It's not moving, right? And then on the bottom here, we are actually applying some traction. And then, so we can actually represent the displacement by using the mesh points, right? So this is how it looks like. And so all these little squares that you see, that's basically your finite element pieces, right? So finite element. So in this one, I forgot how many nodes it has. Probably, I don't actually know, 100,000 maybe, or 50,000 or something like that. So that's basically what you're looking at. Okay, so now going to the inverse problems. That's the problem that I'm interested in. So that's not many people actually do, but there's communities. So the inverse problems, if you're hearing about inverse problem, there's going to be people who are doing something similar to this, but there could be also different kind of problems, right? So it is a kind of a general umbrella term, but inverse problems in PDEs. So that's different from those. So here, elasticity imaging or elastography inverse problem is something where we are looking for the tissue stiffness parameter, right? So the thing that we are going to have, or we are going to have at our disposal, is basically the displacement data, right? So the use that we were talking about earlier, so that's what we're going to have measurement of. So maybe we will have measurements of this U at all of these locations or some certain locations at these on this grid, right? And then, so what you're trying to find out, you're going kind of backwards, right? So it's like you have answer to something, right? You got that. Now you're trying to find out what the question was, right? So that's inverse in that sense. So here, now the idea is apply a small compression force to the soft tissue. And then you're going to have ultrasound images. Then from there, you will be getting the displacement fields. And so that's, I think, what imaging scientists do, I believe, right? So you're working with images and extracting displacements. So I heard that it's image registration, I believe. So I don't really do that. So I don't know how it works. What I have is I do have displacement data. Sometimes we are provided by certain lab experiments. Occasionally, we make up our own data, so synthetic data, to test our solvers. So here, main point here is that to recover or estimate the tissue stiffness parameter mu from the measurements of that U, right? That displacement components. Okay, so here I'm really talking about how we actually create data. So one way of doing is that you just find out or choose a mu, function mu. Maybe some places it's stiffer, some places not. So contrasting function, choose that. And then just solve the forward problem because it's easy to do, it's well posed, and a lot of people actually do. There's tools available. And then maybe get the data by maybe adding some noise, right? Noise to it. So that it resembles an actual data. So you can do that. And so the other one that we have actually used that some of the biomedical engineering or imaging scientists, I believe, right? So one of the labs actually has to do with imaging. So they actually do make these tissue mimicking phantoms. And then they do apply those ultrasound, get the images, extract the displacement data. And then what they will typically have is that they have kind of carbon inclusion inside a solid material, so silica, gel, all those things. So that's, phantom data. So that's something that we have access to, but we don't have any access to any sort of medical actual data, right? So this is how we test them. So how do you solve an inverse problem? You have to make it basically an optimization problem, right? So what we have here is that this Z is actually our data. So that's the displacement vector function. So measure it, given it certain locations in your domain. So it's discrete, right? So we have this data. And then now what we need to make sure is that we need to find out a mu, the stiffness parameter, that for which the corresponding displacements are really good match for this measured data, right? So you're basically trying to make this difference minimal. So you're trying to make this mu and choose the mu, find the mu in a way that the corresponding displacements for which we have to solve the direct problem, right? Matches the data that we have very well. So this is one of those most common objective functional or loss functional or misfit, right? So think about least squares problems. You know probably them in discrete setting like curve fitting, right? This is just a kind of extension of that one in function space, right? Because we are dealing with functions. Okay, so here, just emphasizing that U mu is the solution of the forward problem for a particular choice of mu, right? This is called OLS, or output least squares. So that's basically the root mean square, so extended into a function space. The one that you know from curve fitting, right? Okay, so here, just showing you what kind of things does it lead to. So actually, we are using a different loss functional. So this is called energy least squares. OLS, there's some disadvantages when it comes to using that for optimization problems, because there's lack of convexity, for example, right, to concave up, or uniqueness of a solution. So there's some mathematical conveniences in using loss function that kind of looks like this one here. So here, basically, you see that difference still here. But now, one thing that this functional or this misfit functional differs from the OLS is that it actually does contain the unknown parameter kind of explicitly in the function itself. So there you see that mu, right? So here, I'm just showing you what does it mean to actually compute that particular difference, right? So in a discrete setup, that's exactly what we have to work on. So this is your data components, right? And so what you would be doing here is that for a particular given choice of M, that's the coordinate vector corresponding to your mu. So you will be solving the Dirac problem to get the U, and then you will be looking at this difference. Now, the difference here is that you do have this A of M matrix that's actually appearing in the evaluation of this loss, right? So that's how it looks like in discrete form. So for this one, this OLS here, you have slight difference there. So the difference here that you're not going to have, here you're going to actually have just mass matrix or some another matrix that does not actually depend on the parameter itself, right? So there's some mathematical convenience for this one. You can prove things easily. So you can, for example, talk about convergence or uniqueness, right? Or how your numerical method that you design actually works, right? So that's the reason that we take functional that looks like this. And so A of M is the one I kind of briefly mentioned earlier. So if you look at that stiffness matrix, right, there's this part that is the block. This is a block matrix, right? And so that one comes from this one. So it has to do with the original model. I can go back. So this is the one actually, this one discretized, right? If you discretize this one, put your basis function expressions in there, and then assemble the matrix, then you get that A. It's a fixed block, yeah, it's fixed block. Once you have the mesh, you know the dimensions, right? So, but every time when you change your mu, that matrix is going to change, right? Exactly, yeah, yeah. That's how it's going to be. Okay, so I'm going to show you some pictures now. So once you have an optimization problem, now you need to make sure that you're solving the optimization problem together with that finite element PDE solving, right? So it's basically a combination of optimization methods and numerical PDEs. So you're combining them into, this is just one of these gradient descent method variation. So here we are just using a constant step size, for example, to speed up things, because finding out these step sizes, well, that's what people do for gradient descent. So it does take actually a lot of time. But if you choose the alpha, and we don't have a particular specific way of choosing, it's problem dependent. And so it works as well. So, but there's other variations as well. You can use like batch gradients instead of using a complete gradient of the objective function. You can use batches, and so on. So again, computational cost is one of the things that we care about. So we did a bunch of experiments with that. And so here are just, this one is actually nothing too important. So again, so just making sure that your direct solver or the forward solver actually works. And so here you're seeing one of the meshes. If you have 16,000 little squares in two-dimensional domain, right? So this is how the dimension of the U vector is going to look like, 148,000, right? Because for this particular problem, we are using piecewise quadratic representation for the displacement. So here, another thing that I just want to briefly mention here is that adaptive mesh refinement, that's something that's really necessary, especially for this particular problem, because what we need to do is we want to actually recover that boundary of the stiff and soft and regular healthy tissue and stiffer tissue properly or more accurately. So a lot of the times what we need to do is we can't just use mesh that has all these same little squares. In some cases, we have to really go into more finer. In places where it's not varying or changing more rapidly, we could actually afford to have larger squares or rectangles, right? So that's the idea of this one. And I think I will actually just go. So some numerical experiments, that's something that we need to show. Yeah, so here just kind of, you can choose functions that are kind of smooth, not like abruptly varying, discontinuous, that looks like this one. So here, this is meant to have, maybe there is some more stiffer tissue in this area, but the change is like gradual, right? So two locations. This one is meant to have this transition that's almost like a discontinuous there. So here, large value, and maybe here surrounding softer tissue, or maybe you might have, tissues that are kind of still sort of contrasting here, but different sort of values for the mu. Maybe it's not as stiff here as in that one, right? So you test your solvers by using that kind of synthetic data. So the idea is that you just basically feed this into your direct solver, get a displacement, add some noise, and then go back and see if you can actually recover that, right? So pretend that you don't know this problem, and then see if you can actually recover that by your inverse solver. And then, so this is one example so this is the exact one so that you're seeing on the left. So just the view from the top. And so this is how the estimated one actually looks like. And so we can say that we can recover these actually quite easily. even using, uniform meshes, that means all same squares, right? That works. And so here we are just using the adaptive mesh refinement technique over here again. So it's because the changes are gradual, so that it doesn't really, well, it's refining in some places definitely more, in some places less, where the solution is not changing too rapidly, but it doesn't make too much difference. We can still recover these by using uniform meshes. And so, but when it comes to a parameter that looks like this, there's like a discontinuous change transition, right? So this is a stiffer part, and that's the softer part. And so there's two locations here. So for that, you start actually seeing some differences, right? Because here you see that the boundary of this, the transition is actually not properly resolved if you just stay with the uniform mesh. So, and if you want to make it, resolve better, you would have to refine your mesh a lot. So that means your size of your system is going to be really large, because the optimization problem dimension is equal to approximately the number of mesh nodes in the system. So that's going to be really very time consuming, right? So you need to really kind of think of ways of reducing that cost. And so that can be done by using something like this. So this one is actually corresponds to adaptive mesh refinements. So here it is at some point before you actually stop and you're happy with the solution. So somewhere in the meantime, and so this one is how it looks like if you use a mesh that I'm going to show you in the next slide. So here you see that it is refining the mesh much better right around the boundaries, right? And in other places, it's basically almost coarsening, right? So that's how you basically resolve these, right? So you get definitely better accuracy with less or smaller dimension of the optimization problem. Right? I should probably, okay. So here we just did a few experiments with tissue mimicking phantoms. So this is the one that we actually took from the website of the Impact Lab. It happens to be an image processing characterization of tissues. So that's a lab description. So it's Concordia University. And so we basically have displacement data that we can download. And so here, situation is like that we have one or two hard inclusions in the phantom. And so the Young modulus values at least twice, so that's kind of the contrast, I guess. And so the phantoms are made by synthetic materials, so there's some description over there. So again, the idea is to kind of mimic that, properties of the biological tissues, right? And so here, this is how the data looks like. So if you look at the displacement components, so the first component, if you plot that, this is how it looks like. Second one, this is how it looks like. And you kind of start seeing sort of inclusion over here on this one, actually, right? A little bit there, the blue area. And there's another one. This one is supposed to actually have two inclusions in them. And you kind of see a little outline over here, the inclusions as well. But the actual stiffness parameter, this is how it looks like. So this is the hard inclusion that we are talking about. Again, we had to really compress kind of our data because the dimensions were really big. So our laptops couldn't handle them. So we kind of made the data more smoother, every 5 points or something like that. So, but still we do actually have really good recovery of these contrasting tail properties in there. Right? Okay, so that's almost it. So the thing that we are doing is that we build up basically kind of a general computation framework, integrating of the PDE solver and optimization methods. And so main priorities for accuracy of the recovered parameter, we want to resolve these properly, and then while also being mindful of the computational cost as well, because it's a large scale optimization problem. So there's this huge path, this optimization. You have to solve your forward problem at every iteration doesn't actually help, right? Because that's a PDE solver that we have to be doing every time. And then, so we can basically show that it can handle some realistic data and situations. And that's most probably it. So these are my students who worked on, so she's the one who actually worked on this one, Rachel. And so Rachel is a student, was a student here in the math modeling PhD program. She's graduated this spring and she's working at the pharmaceutical company as a quantitative pharmacologist. And so that's another of my students who also graduated from the program this summer. So credits to them. They worked really hard for this kind of stuff. And so looking forward, we definitely need to have some quantitative results for the accuracy of the estimation. So that means we need to show maybe there are error estimates. So this is how it works. That's how it's guaranteed to work and so on. So there's big part that has to be done. And other variations of the methods, stochastic gradients, something that uses gradients because they are quite efficient. And there are also other issues such as computational parameters, model parameters, how they interact with each other. And then also there are a lot of parameters that we need to choose and calibrate as well, right? So like the step lengths in the optimization method or regularization parameters. Regularization is something that you need to do if you're solving inverse or ill-posed problem. So that's it. And I think I will stop here and see if anybody has questions.
It's actually very interesting.
Yeah.
Go ahead.
Actually, working on classification, I read something about finite elements are using sampling. So it might be relevant.
Does it have a PDE?
Oh, yeah.
No, yeah. Okay. Yeah.
This is very relevant to adaptive optics.
Adaptive,
So I did a deformable mirror design. If some of you are familiar with adaptive optics, you poke the mirror and you see the influence function. That's exactly the same you're doing that. You poke the tissue, you measure the displacement, and you try to get the stiffness. But for deformable mirror, you know the stiffness already, but you don't know the actual location. And that's a problem you're trying to get inverse. So it's very relevant. This is just my resonance with that. I hope the students can find the good application. What's your name?
Spencer,
Spencer?
if you have better data from like medical laboratories, would your models be better or can you be able to fit them?
So we can definitely try. So the model is set up in a way that you can take the data, read it, and then put into you can create the meshes that's corresponding to you can create a mesh, and then you can try to solve that. And because we never tested it for medical data, with actual data, so I don't know how it depends on how the formatting. So for this particular one, I think we just had like a matrix of values for the displacement. So it was kind of really easy to kind of match. Okay, that's the top one, that's the bottom one. We just created a kind of a really simple uniform mesh that worked out. But depending on how the data formatting looks like, we might have to do a little bit of work to create the mesh that corresponds to, or maybe you could just connect them and create a mesh, right? So in principle, it should work. It needs definitely a little bit of work, but it might work. But we need to test.
Yeah.
The calculate the stiffness, the PD, is that the Helmholtz equation that you're using, or is it something different?
It's not Helmholtz, but it's, so if you were just working with like, so there's, for example, the same kind of thing that one of my students actually did, she actually did for a heat equation, right?
Okay, yeah.
So it's like really like Helmholtz, right?
Okay, yeah.
So, but for this particular problem, it's linear elasticity system, so slightly different structure, but idea is same. They're both elliptical PDEs,
Sure.
right?
Yeah,
So, yeah.
And then I'm assuming you're doing direct conversion. So And my question is like, because especially for medical system, especially when you look at real data, there's gonna be a lot of noise. And as you propagate it through especially the inverse problem, it kind of, increases the noise as well. So is there a better way to
Yeah.
handle that?
That's a really good question. Yeah, so the noise issue is one of those big things that we never really done. So we are not doing direct conversion, by the way, it's different, right? So we are actually doing regularization, optimization plus
Got
regularization.
it.
So,
Sure.
yeah, so, we do regularization, but noise is still, okay, it's quite sensitive to noise. So what we have in our experiments is like really like 1 to 3% noise, right? So that's, and then some of the objective functional and loss functions, they're more sensitive to noise than the others, right? So that's also another one, yeah. But that's a really, really relevant and important part. We have never done anything like that, but we also tried like things like smoothing the data and things like that, but it didn't really help too much. So it just messes up because I guess we don't really know how to smooth. So, okay. So, yeah, I was just talking to my students who are in a grad course recently. So they are also, I tried to tell them about this computer tomography English problem. They're, sending X-rays and, using the intensity loss. They're trying to find out what the image looks like, right? So they actually learned about some vulnerability and stuff. Yeah, so yeah, we know really well about the noises, how they
Okay,
can
yeah.
actually affect these problems. Yeah.
What program do you run your simulation with?
So this deal 2 is open source finite element library, and it's actually C++. But there are a lot of other, finite element libraries that you can use, like there's FreeFan and I don't know.
There's a
bunch of other.
Ansys, there's console.
Ansys console, yeah, that's finite element simulations. All our engineers do console and Ansys. So,
Yeah, my lab has
Yeah.
console. They use Ansys as well.
yeah. The one that I use this deal to is, there's a little bit of more control of what you can do, so you have to do actually a bunch of coding. It's not quite as like black box, right? Some of the programs of packages, they are more like black box, do certain things, but here you can actually do and go a lot of things like building optimization software based on that. So it's more flexible, so I think show something like that.
No other questions? So we know Professor Jadamba just at the math department. If you have other questions,
You see
maybe.
you were in Michigan once?
Oh, yeah, I was actually in Michigan Tech, which is the Michigan Upper Peninsula. I was just there 1 year. teaching at Michigan Tech.
I'm from Michigan. so
Oh, you are?
that's like one of the-
So that's Michigan Tech in Halton. It's like really
I'm from
tiny
Michigan.
university town, right? So
So
6,000 people, I don't know, something like that.
Yeah, so you can find her contact easily, reach out to her. for-
If you have more questions, yeah. Okay. Thank you.
Other than that, I think our, I can.
This up.